Okay, so hi everyone. We'll get started there tonight. Hopefully, some of the rest of them will join us in the next few minutes, and if not, they can watch the recording. Just start with a little bit of good news, which is to my best estimate, I think we're about 2/3 of the way through the material for the year. Despite the fact that we're only coming on to, I think, week 7 at this stage, so we can throttle back basically to about 1 hour per week, I think, now for the rest of the semester, or that's my hope anyway. Don't hold me to it, but that's what I reckon we can do. So that should ease things on you a little bit, particularly with all the assignment work and so on that you've come up to at least know that you're well over halfway and probably 2/3 of the way through the material. So the next number of lectures are on what this subject is all about, which is the multi-view geometry part of the computer vision, and everything else is kind of leading up to those. So what we're going to be looking at in the first case is we're going to be looking at the situation where we just have two views or two images. And from then we'll move on to what happens if we have 3 or more images, which is a good deal more complex of a case, and it has certain advantages over the 2-view case. But really, nailing the 2-view case will be a very important part for you. So this will be in 2 parts. So the first thing we're going to do is we're going to try and find out the rotation and translation between the 2 views. And then in next week's lecture, we're going to look at how from there we can try and figure out the 3D geometry or the 3D coordinates from that. There'll be a few other parts next week's lecture as well, but that'll be the main idea. So to start, what we're going to do is we're going to start with some opening assumptions. And this is always slightly important when you're doing any of these things, that you state very clearly what's the opening assumptions that you have, so that you constrain the problem. Because if we just leave it completely unconstrained, as in a general real world problem, it normally becomes too difficult for us to solve. So we start with a constrained problem, and then we can start to look at edge cases and start to build it out from there. So that means starting with some opening assumptions. So to solve this problem one step at a time, we need to make some assumptions. We have to assume that we are viewing a static scene and that we have 2 different views of this scene. So what we mean by a static scene is that nothing in the scene is moving. Okay. Now, clearly, if you're in an autonomous vehicle, other things will be moving. And with the situation that we're dealing with here, we will normally assume that it's actually the same camera in the 2 views, so there's some time has passed in between it. That is a problem, but nonetheless, we would hope that when it comes to actually being used in the real world, that the time gap between each of these will be relatively small. Okay, but we start with these opening assumptions that nothing in the scene is actually moving; everything is static. We will assume that we already have a set point correspondences in our 2 views. So hi Niall, good to have you in. So we'll assume that we already have a set of point correspondences in our 2 views. How we did this is not our concern in this section. So all we're just going to assume is that we have a set of point correspondences, and I'll talk later about how many of those that we will have. So we assume that we know the intrinsic parameters of the camera. So in other words, we know the focal length, and we know things about the width and height of the pixels and so on, or the scaling of them. And we'll assume that they are the same for both views, which is a reasonable assumption in many cases, because particularly for the autonomous vehicle or something, we would normally have the same camera in both places if it's a stereo setup, or if it's one front-facing camera. Then normally, as we move from one place to the other, our 2 views come from the same camera. So that's also a reasonable assumption. But in the much wider case of multi-view geometry, that might not be a reasonable assumption. So there are examples whereby people have recreated famous landmark buildings purely from getting images off the internet. And of course, all of those will be taken with different cameras, different focal lengths and so on. But nonetheless, they can build it up from there. For what we're doing tonight, we're just going to assume these different things. So keep that in mind as we go. So what do we not know? Even with these assumptions, we still have a problem on our hands. We know a set of 2D points, but we don't know the extrinsic parameters In other words, and the extrinsic parameters are the positions of the camera in both where it's taken both its images. So we don't know the rotation and translation that is taking place between those two views. We don't know the 3D coordinates that correspond to the points in the images. So all we've got so far is just points in images, which are 2D coordinates, and we don't know the main things that we really want to find out, which is how has the camera moved in between these different positions, and what are the 3D coordinates that we're looking at. Because obviously the final thing that we want to get to is we want to be able to get to 3D coordinates that we can actually see. Okay, so to find the extrinsic parameters, rotation and translation, we need the 3D points first, okay? And to find the 3D points, we need to know the extrinsic camera parameters, so we need to know the rotation and translation. So you should see from those two sentences that there's a problem there, okay? We need one to get the other. So this is usually referred to as a chicken and egg problem, or as a catch-22, where we're trying to separate one from the other. So the route to the solution is as follows. We would disentangle the 3D coordinates from the camera motion. So and we do that algebraically. So in a linear algebra way, we would try and separate out those different terms from each other. So we need to be able to see the rotation, translation, and the 3D coordinates as separate entities within our algebra. Then what we want to do is we want to remove one of these, and generally our way of doing it is we're going to remove the 3D coordinates from the algebra so that we have equations in 2D image coordinates only. So very much like when you're dealing with simultaneous equations and you eliminate one of the variables, we're going to try and do something similar here, in that we're going to try and eliminate one of the problems that we don't know the answer to. We're then going to try and use these to solve the camera motion. So we're going to try and figure out our rotation and translation from there. And we're going to do this using a thing called the 8-point algorithm. And now that once we have that, we have our rotation and translation, which are our extrinsic parameters. We can then determine the 3D coordinates from there. Okay, so once we have that, we can kind of go back to our original formulation. We now have one of the pieces of information that we needed, and we can work from there. So the 3D coordinates, once we have them, they are the reconstruction. Okay. So note that what we're going to do tonight is we're solving a neat mathematics problem. And just a gentle reminder that the real world is not a neat mathematics problem. So all the time we're going to be looking at what are the different things that could make this problem not work nicely for us. Okay. Have we a few more in? Oh, we have. Okay. Okay, so this entails we're going to come up with a thing called epipolar geometry. So we'll continue to call a point in the 3D world large x. So we'll just call that large x whenever we're dealing with it. The projection of this into the first view, okay, so we'll call these the first view and the second view because we're only dealing with two views. So the projection of this 3D coordinate into the first view results in a 2D coordinate which we'll call x1, and its projection into the second view results in a 2D coordinate called x2. Now later in the lecture I'll change their names to x and x prime. The reason I don't do that at the beginning is because I want you to just get an understanding of the equations, and when you've got all those little primes in the middle of it, it can be difficult to make it out. So later I'll change them for a specific reason when we come to it. For the moment, you can assume that it's the same 3D point called x, and it's projected into two camera views, and the position that it's in the first camera view is called x1, and the position in the second camera view is called x2. We refer to the center of projection of the two cameras. Okay, so the central point there as O1 and O2. Okay, as because they're the origins that we're going to have. So we have the origin in one camera and the origin in the second camera, which, as we spoke about last week, we would normally assume as being the pinhole of the camera. If we draw a line between the two centers of projection, this line will intersect the two image planes. The points of intersection are called the epipoles, which is where this idea of the epipolar geometry comes from. So epipoles E1 for the intersection with the first view plane, and E2 for the intersection with the image plane of the second view. And one thing to note is that these intersections do not have to occur inside the small rectangle of the image. What we're assuming is that when we're taking a photograph and we've got our rectangular view there, that plane continues forever. and at some point the line is going to cross it. So the image planes are assumed to continue forever in all directions. So we have a diagram of what I've just been describing here. Shout out to Mubarak Shah from University of Central Florida, where I got this diagram from. And if you click on that link there, if you click on his name there, that should bring you straight to the point in the YouTube video where he describes this. So if you want to get another explanation of it from this guy, you can go and do that. So let's have a look at what we have first of all here. We have two cameras there, and they're both looking in some direction, and we have a point. Now he's called it P, but if you remember, we've called this 3D coordinate, we've called it large X, and we've called our coordinates in the image, we've called them X1 and X2. Okay, but other than that, it's perfectly fine. So he hasn't really, it's not really any different, just a slightly different notation. So we've got a point in the 3D world there, and that has been projected into two of the cameras, okay, or into the two cameras. Now remember, what will normally happen is that we just have one camera and they've been moved from one place to the other. Now, what we have is we have a line that traces from the center of the first camera to the center of the second camera, and that's this line that goes along here. Use a smaller one there. That's this line that goes along there, from there to there. Okay, and where that crosses the image plane in both cases, those are our two, what we call our epipoles. Okay, so the epipoles. Now they're not necessarily in the same place in both cases. Now, in effect, you can think of that intuitively as if we were in this camera view, okay, our epipole, where that's positioned, would be where we could see the second camera. Okay, now remember that in most cases we're actually dealing with just one camera, so therefore you're not going to see the other camera. And secondly, even in the cases where you use two cameras, you normally don't have them appearing in each other's views. But nonetheless, if that only means that the edge of our frame did not continue on long enough for it to appear in the frame. In other words, the frame just wasn't big enough. If our frame was infinitely large, we would see the other camera within our view. So that's what that is, what the epipoles are showing. We also have these things called epipole lines, or epipolar lines, which are the lines that are going from a point to the epipole for a particular point, and we've got another one of those there. Now they're an interesting thing because what happens is that when we have a point here, any other points along that axis between that and the center of projection of the camera will all appear as the one point. Okay, so we can't tell those apart. And what I'll do, maybe just I'll flick to my camera view here so I can see my own camera, because my camera view is actually off here to the right. So the situation that we have is that if I take my pencil here and I point it directly at the camera there, we can just see one point. You can't see all the different points along it. Okay, but if I move the camera view, and I'll move the camera view just like this. Okay, now I haven't moved the pen. You can now see a set of dots along it, or there are no dots on this, but you can now see a full line that occurs there. Okay, so that's turned into a full line, and if I move it back to where I was, if I can do that without breaking my computer, it comes back down to a single point again. Okay, so that's in effect what we have here in this situation. This is you could imagine my pencil as being along in this direction in the first view, and we can only see one dot. But if we're looking from the other camera, we can actually see a full line going on there. Okay, and that line that we can see there, that line is going to appear, or if we were to follow that, that line appears in our image. Okay, so where you could see the pencil, that line appears to go along in a direction until a point where it's also going to hit that epipole. So we may not know where we are here, but we can actually follow along a line that's going to find us those as well, should we need to do so. Okay, so that's the idea there. Now, those are the epipoles and the epipolar lines, but the last thing we have here that we want to discuss is the epipolar plane, which is the bit that's shown in green here. And this is a very important concept for what we're doing tonight, because what this is saying is that we're in a three-dimensional world, but we know that if we see this point here, and it appears in two of our images, it appears there and there, from that information and from our epipolar line, that is, or sorry, from this line that's joining these two here, we can see that this forms a plane. Now that's not that's maybe not that obvious, but in effect what that means is that if I'm looking at a single point, they're going to match up, and then I've got this line in between there, that's going to form a plane in the three-dimensional world. And planes are two-dimensional, but they're inside a three-dimensional world, and we're going to be able to use that information in order to track down, well, exactly where should that point be. If we have any error in our measurement, which of course can easily happen, what can occur is that we end up with a situation like this, okay, where we're not exactly meeting. And if we're not exactly meeting, then we don't have a plane either. We have something else, okay, which would then have a volume associated with it and so on. So that's why when I say that this is a neat mathematics problem, but that there are some issues with regard to it, if we have noise or anything like that, if anything goes wrong, any sort of distortion, that we don't take account of in our mathematics, then we may not get that plane, and from that we may not be able to get something that has that is two-dimensional but within a three-dimensional world. Okay, so we might need to pop back to that diagram from time to time, but for the moment, at least you can kind of keep that in your head, that diagram. So a triangle is formed between the 3D point X and the two camera centers. This triangle is said to lie on the epipolar plane. The intersection of the epipolar plane with each image plane is called the epipolar lines, and we saw how they would appear within the image. So we'll call them L1 and L2. And there is a single epipolar plane for each 3D point, which we'll call, so each 3D point X, there is a plane that's associated with that. So we have, for each 3D point, we're going to have a set of correspondences between the two images, and between all that information we can form this plane and we can work from there. So, quick linear algebra reminder, a 2D plane in a 3D space is called a subspace. Now that's assuming that it passes through the origin, but we can work around that problem as well, even if it doesn't pass through the origin. We can define the plane with vectors that lie in the plane. Okay, so oftentimes if you have two vectors, let's say you have a vector there and a vector there, which we'll just call, I'll call x1 and x2. From there, I can use any linear combination of those to fill out an entire plane. Okay, which means that if I want to get to some point down here, I can actually do it by just saying, well, I'm going to need, let's say, minus 7 of x1, which would bring me, let's say, all the way over to there. And then how many of these am I going to need? Well, I'm going to need a certain amount of them, but they're probably going to bring me way down here. So maybe I need to go only 5 of these and start here, so that it brings me down eventually until I land there. So even though I haven't drawn that particularly well, you can kind of see that from any two vectors that are not the same as each other, you can actually fill out a full plane. Okay. What we can't do with those two vectors is I cannot get off the page. Okay, so I can't rise up here into the space above it. So we can define the plane with vectors that lie in the plane. Two independent vectors in the plane will be enough. The ideal situation is when those vectors are orthogonal to each other, because we can then very easily get to wherever we want to go. But any two vectors will do. But we can also define a plane by a single vector that is orthogonal to it. Okay, so in the case of this, I would actually have to have it pointing out of the page. Okay, but a single vector like that will tell us that plane. Now you might say, well, how does it know exactly where my iPad is here that I was writing on, or my sheet of paper? Well, it doesn't need to. The plane is the entire 2D plane that goes forever in all directions. Okay, within our three-dimensional space. So therefore, if we have a single vector that's pointed orthogonal to that, which we call the normal vector, then we have enough information to define that plane. Normally that is at the origin, so that when we but it doesn't necessarily have to be either. As long as we say if we project that vector, sorry, it would have to be at the origin in order to be pointed straight up, right? But if we project that vector onto the plane, it comes down as 0. So you get that 0 point down below it is the idea. Okay. So we can define a plane by a single vector that is orthogonal to it, i.e. a vector that is in its null space. Now, have you come across that term null space before? Now, I may have mentioned it, I can't remember, but have you come across it in either in the linear algebra subject that you did or anywhere else? Okay. Nobody's saying no anyway. Yeah. Okay, so it's something you may need to go back and do a refresher on. So what I can do is I can maybe you can look at Gilbert Strang's YouTube videos, the 1806 lectures from MIT, which are excellent in terms of going through these. So there are a few things that are going to pop up quite a bit tonight and for the next few nights. So if you're having trouble with them or having trouble with the conceptualizing them, it's worth your while going back and spending a bit of time on them. So those are things like the null space. Singular matrix, I think you all know what they are. A singular matrix, what would the determinant of a singular matrix be, for example? Okay, nobody's biting on that. Vin is typing here. Oh yeah, Niall has said it actually there. So Niall has said it is 0 indeed. Okay, so it is a 0 determinant. And so if we take, for example, the 2D plane that we had in a 3D space there previously, that would have a 0 determinant because it has no volume. Okay. Now, to have a 0 determinant, you end up having a thing called a rank deficiency. So I assume you've come across the rank of a matrix. So if we have something like a 3x3 matrix and it is only of rank 2, then we have a rank deficiency. So if we don't have full rank, then we also have a singular matrix and so on. But rank works a bit further than that, because if we have rank 2, it means that we have a null space of 1, and that turns out to be important. So 0 determinant you've come across, and I think you did singular value decomposition, did you, in the can you answer me on that? Did you do singular value decomposition? No. No. Okay. We definitely need to get you maybe some videos on that, because that's going to come up tonight. But I'll get you to look through it after this. Okay. So it's a little bit like getting the eigenvalues, except you're getting the eigenvalues of something that isn't necessarily a square matrix. You did it for the assignment in maths. Okay. Assignment, that's perfect. Okay, so there's a few things there. I might send you some videos just to watch in the meantime, to try and get yourself up and running on some of those things. They're going to come up tonight, so if you don't fully follow them, don't panic, but do go back and try and get a sense of them later on, because they come up again and again and again as recurring themes. So what we're going to do is we're going to simplify things for ourselves by simplifying the intrinsic parameters. Remember I said that we're making an assumption at the beginning of the lecture that we know the intrinsic parameters of the camera. So firstly, let's deal with these parameters. We'll assume no skew in the pixels, and we'll assume a 1-to-1 aspect ratio of the pixels. We'll assume the focal length is 1, okay, for the moment. This idea of setting the focal length to 1 is just a way of saying that all other measures will be in units of the focal length. So rather than giving sizes in millimeters, centimeters, or meters, we instead give everything in units of the focal length. And because we're assuming the two cameras are the same, they're going to have the same focal length. We can then convert everything easily if we do know the focal length later on. And we'll assume that the origin is in the center of the frame. So the camera intrinsic parameter matrix will be just like this. K equals fsx, fsy, and our two origins. Basically what we'll just have is we'll just have a value of 1 for fsx, 1 for fsy, and we're going to assume that our origin is at 0, 0 in the center of the frame. So they're both 0, 0. And so basically what we're going to have is we're just going to have an identity matrix. Okay, now that simplifies things greatly for us because we really want to worry about the extrinsic parameters in this particular set of the lectures. So we're going to assume that this thing is perfect. Later on, if we don't know them, I'll show you how you go about that. So that's the identity matrix, and this allows us to leave out entirely our mathematical manipulation because, of course, once we multiply any of the matrices by the identity matrix, it's just going to end up the same. So we can pretty much leave it out. So x1, which remember is the projection of the world 3D coordinate point onto the first camera image, x1 will be in homogeneous coordinates, so we'll work with everything being relative to the first camera view. So what we're going to assume is that the origin of our world is actually in the first camera view. Therefore, there will be 0 rotation and translation, so no intrinsic parameters to worry about in the first camera view. We assume it's where we start from, it's our relative point. So the mathematical description of the first camera view is actually very simple. All we do is we take our 3D point and we say it's x1 multiplied by some scale factor which we don't know. So if we have a kind of our 3D world here and we've got our camera view looking at it. So we're looking at some point here, and then this is going to be our lambda 1 here, which of course we don't know, and these are some of the things that we're going to have to try and figure out later on. Okay, so that's and it ends up as being a pixel here somewhere in this image. Okay, so that's our first one. For the second camera view, we must describe this in terms of camera 1. So we're going to say, well, what's the rotation and translation from camera 1? So this means a rotation and translation of the 3D point followed by the projection. And remember that the projection, because it's only the identity matrix, we're just going to have the projection to some other point or some other distance, lambda 2. So going back to my diagram here, that would be that we would have another one of these rotated in some way. Say, and we have the view coming down like that in some way, and we've got a lambda associated with it. So we'll call that lambda 2. Okay, this is my second camera view, and of course what we've done is we've rotated here. We've rotated, and we have and some translation between that point and that point as well. Okay, and we'll have done some translation which we may not see. Okay. So, so we do that by saying that what we're going to do is we're going to take the original 3D point, we're going to rotate it and then add a translation, and that now puts us in the coordinates, in the coordinate frame of the second camera. And then what we have to do is obviously we have to take whatever the distance is that that we are away, and that gives us x2. What we can do is we can substitute equation 1 into equation 2. So equation 1, remember, was this one. It was lambda 1 x1 equals x. We have that x there, so that's going to give us the following: lambda 2 x small x2 by or equals or, sorry, by so the rotation by lambda 1 x1 plus the translation. Okay. So keep typing away there, Vin. I'll keep an eye on it. No, we're not tracking objects here, so we're assuming that we're looking at a static scene, that we have 2 point correspondences that correspond to a single image point. We're assuming we have all that, and all we're trying to do now is to try and figure out how our cameras have moved. So in the last lecture, maybe that you're mixing it up with, we were trying to track something moving within an image. In this case, we're assuming we know the 2 points that that correspond to the point, and we want to know how has our camera moved. So if our camera's on the edge of our thing here, has it moved from there to there? That's what we're trying to find out in this particular case. So it's a different problem that we're trying to solve. Yeah. Have I a picture for reference? Yeah, it's this picture back here that I showed you there. Okay, so this one here, what we've done is we've got our central point. Okay. Oh, sorry. Great. How do you pick a reference? Is that what you're asking me? Yeah. So so when you say reference, are you referring to our 3D point here? Is that what you're asking me? The 3D point. Okay. So all that happens is we're assuming at this point that we have 3D points. And if you remember in previous lectures, we looked at how we would get point correspondences between images. So it doesn't matter what our point correspondence is. And later on, we'll see how many of these do we need. How many of these do we need in order to be able to fully figure out our rotation and translation? For the moment, we're just dealing with one single point, and it doesn't matter what the reference point is, as long as we know, as long as it's there and it has appeared in both camera views. Okay. Okay. So that's our point, and this is the equation that we've now ended up with. Okay, which is lambda 2 x2. The rotation times lambda 1 x1 plus the translation. Now, work away there, Liam. If you have a question, we've got plenty of time tonight. So, as I say, we're going to be throttling back. We'll only kind of need about an hour and a bit from now on for the rest of the semester. So if you have a question, feel free to ask it. Yeah, so the translation will give the distance from the two camera centers, and the rotation will then tell us how much we've rotated by. Okay, and in the 3 dimensions we can rotate in, remember, not just in 1. Yeah. Okay, so the translation alone will give you that distance there, as you can see that in the diagram there. The translation alone will give you that, but then we've obviously rotated the camera as well in the second view. Okay. So, and keep going there, Niall, and I'll just keep going here while you're typing. So, what we want to do is we want to get rid of that translation. That's a convenient thing to do because it'll make things easier on us, right? And the translation is a 3D coordinate, or sorry, it's a 3D coordinate, or 3 dimensions to it. So what we want to do is we want to remove it, and we're going to use that system that we came up with later. Terms, would we use this technique for localization of so the question Niall is asking, in practical terms, would we use this technique for localization of the eco vehicle? It depends on the situation, right? So if you know some 3D points in the world and you could actually find those, then you could do that. But much more likely what you're going to be trying to do is you're going to be trying to see from your point of view what are things in your vicinity. And you'd maybe use something else like GPS or some other sensor to tell you roughly where you are. So it's kind of like, you know, well, I know roughly within, let's say, a meter or a foot or a few inches or a few centimeters where I am. Now I just want to be able to see my way through the environment. So we would be able to tell where we were in comparison to other things, but you wouldn't necessarily want to use it to decide where you were in the world. That wouldn't be the best system for that, because you then need to know all the mapping about the world and how those 3D points would relate to it. So why do we need to know how the camera moves? Because that will help us in figuring out the 3D points. So if I want to, because I've got 2 eyes here and there's a gap between them, my brain has figured out how to use that to figure out where things are in 3D. So I need to know the positions of my 2 camera views before, from then, I can figure out my 3D points. Okay, in order to build that up. Okay, so Vin is asking, how do we pick a unique 3D point, or how do we eliminate a duplicate 3D points? So again, that's as part of the other lectures. So you either use the systems where such as the ones that you're doing in the assignment in order to find unique points, or there are other systems that we will hopefully get a chance to look at later in the course, where we give much greater descriptions of points so that we don't tell them apart. But again, as I say, I want to go back to what I said at the very first slide. We're assuming we already have the points. And so I'd like you to kind of stick to that for tonight, that we are assuming we have the points. In other lectures, we deal with the situation of how we make sure that we don't get duplicate 3D points and things like that. That's for a different lecture. So in this case, all we're looking at is we've already got those. We've got the projections of them. So we've got our correspondences between our images. From there, how are we going to figure out the different pieces of information? Is that okay? Yeah, okay. So they're all good questions. It's just in certain cases they're a little bit wider than maybe what we're going to do in just tonight's lecture. So this is the t, which we'll call the t or the cross function. Now hopefully you remember this. This is where we turn a 3D vector. So we'll call this, let's say, u1, u2, and u3, and we turn that into a skew symmetric matrix. If you remember, we turn it into this. Which is can I remember it now? There's minus u1, u2, and minus u3 up there with zeros along the edges, and then we have minus u2, u1, and u3. I hope I have that correct. And if you remember that the operation of this was to do a cross product with a vector. So it was like getting the cross, so in this case it would be like getting the cross product of t with some other vector. Okay, and what we're going to do is we're going to get the cross product of t with t. And what's that going to do? Well, the cross product of a vector with itself is always going to be something orthogonal to itself, so therefore it's going to end up being 0. So what that means is that if we multiply across by the cross product of t across the way, and remember this is a linear algebra operation, I said we'd be using this again and again. So we multiply the previous formula on both sides, we get it there, that's fine, we get it here, it stays there, but here it has the effect of cancelling out that t. So that's going to be t crossed with t is going to give us 0. So we can rewrite equation 4 as follows. Lambda 2 t cross x2 equals lambda 1 t cross times the rotation x1. Okay. Now remember that lambda 1 and lambda 2 are simply scalar values, and they can be moved about more freely than the matrices, which is why that we've ended up with the tx a little bit further in. We didn't just put it on the front end of it there. It's an actual scalar value. We just don't know what the scalar value is, and it's to do with the 3D geometry. But for the moment, we can just treat it as scalar values. And what we want to do is we want to get rid of them. Because if you remember back to what I said at the beginning of the lecture, and I'll just bring it back to remind you, what we're going to do is firstly we want to disentangle the 3D coordinates from the camera motion, which we've already done. We want to remove the 3D coordinates from the algebra so that we have equations in 2D coordinates only. And the reason for that is that to find the rotation and translation, we need to know the 3D points, and we don't know them. And to find the 3D points, we need to know the rotation and translation, which we also don't know. So we don't know either of these things, and we need one of them in order to get the other. So this is the reason why we're going to try and remove those lambdas now, so that we've only got 2D coordinates at that stage. So this next step takes a little bit of explaining, but firstly beware that if we do t cross x2 will result in a vector that is orthogonal to x2. Okay, so if I take any vector and I do a cross product of it with another vector, the result will be orthogonal to both of them. Okay, so that means that I can actually take it that that thing there is orthogonal to x2, and which is one of my vectors. So if we get the cross product of x2 with this vector, we'll get 0. So what we'll do is we'll multiply across by x2. So I've multiplied on that side by x2 and on this side by x2, and what that means is that all of this goes to 0. Okay, because of the fact that we've got something in there that's cross product with x2. If I multiply that with x2 again, I'm basically getting x2 with something that's orthogonal to it. So that's all going to go to 0. And what's the effect of that? Well, the whole lot of that goes to 0. Okay, which is what we have here. Now that's gotten rid of lambda 2. And on the other side, what we have is we've got the x2 transpose, we've got the the skew symmetric matrix, which is modeling the cross product with our translation. We've got the rotation, and we've got the x1 coordinate in 2D. So what we can now do is we can just divide both sides by lambda 1. Okay, so we'll divide both sides by lambda 1, because if you divide 0 by lambda 1, it's just 0. We divide the other side by lambda 1, and we end up with just this. Okay. Now, so this is very important, because what we've ended up with now is we've got something that has the translation, the rotation, our 2D coordinates, both our 2D coordinates in both our views, which we know. We don't know the translation and the rotation, but we can start to figure them out now. The problem was that previously we had them entangled with 3D coordinates, which we also didn't know. Okay, now we've gotten rid of those 3D coordinates. Now we have a path to a solution. So this important solution here is called the epipolar constraint. Okay, so it constrains the x1 and x2 and the tx and the rotation, and this is related to that plane that we saw there in the diagram. Okay, so it's an important result as it relates 2D coordinates without mention of the 3D coordinates. Remember our issue from earlier, which was the catch-22. In order to determine the camera motion, we need the 3D coordinates, and in order to determine the 3D coordinates, we needed the camera motion. The epipolar constraint allows us to determine camera motion without the 3D coordinates. So from there, we can work towards getting the 3D coordinates. So if we take the central part of the epipolar constraint, which is this the skew symmetric matrix, which is a 3x3 matrix with the rotation matrix, it doesn't include the 2D coordinates. We have what's called the essential matrix. So this is E, okay, and it's in the 3x3. So it's a 3x3 matrix because both of these are 3x3. Or is full rank, but the TX isn't. So due to this name, the epipolar constraint may be variously called the essential constraint or the bilinear constraint. Okay, because of the fact that it's related to two vectors. Now, this is called the essential matrix, and many computer vision courses would first start with a thing called the fundamental matrix and would then move to the essential matrix. I'm going to do it the other way around, so you're not going to see the fundamental matrix till next week. And I'm doing it basically in chronological order. This is the way they were originally discovered in the literature. Okay, this is called the essential matrix, and it has both information about the rotation and translation in together. So E is a 3x3 matrix. It's of rank 2. Now, if it's of rank 2, what does that tell us about the null space? Can you remember? I said if it's a 3x3 matrix and it has a rank of 2, how big is its null space? And now you remember from the beginning of the lecture. No, it's 1. Yeah, so it has to make up the third part of it. So a 3x3 should have a full rank of 3. So if you've got a rank of 2 there, it must have a null space of 1. Okay. Now there are things called right null spaces and left null spaces, which you're going to see both of them mentioned here, but both of them will have a size of 1. Trying to think of it. That Gilbert Strang book, which I put in the original syllabus. I don't want to break anything here, which is this one here, which you may have seen. What he's got there is actually what he calls the 4 subspaces, which are the column space, the row space, and then the right and left null spaces. So he spends quite a bit of time on that in his lectures, so it is worth going and having a look at them. So it's going to have a left and right null space of 1. The epipolar constraint stipulates that the triangle, which goes from the origin of the first camera to the 3D coordinate, the origins of the second camera to the origin of the first camera, and the origin of the second camera to the 3D coordinate, that lies on a plane. And this is what the epipolar constraint is actually saying to us, and this is where our rank of 2 comes in. It's the fact that that is a plane by virtue of this. Or we could say that those points alone can define the plane. Now, as these 3 are vectors, we can define a triple product on them. Remember that the triple product defines volume, and a plane should have a volume of 0. So we can say the same thing there, x2 transpose t cross or x1 equals 0. So you can see that the whole thing works out. That in other words, that this is basically saying that this will have a volume of 0 as well with these two. Okay. Now that will only work making sure that this x1 or the x2 and the x1 are actually the same point in 3D space, that you've managed to properly get your correspondences correct. Okay, but we've assumed that at the beginning of the lecture that we have. So this is our picture of this again, just to show it to you. That's our plane there, as you can see, and we've got our two coordinates there, and the epipolar constraint says that you're going to have a plane in there, it's going to have volume of 0, and this is what locks them together. And once again, if we have made any error in our correspondences, we're going to get something where the points don't meet in 3D space, and therefore they don't have a 0 volume. Now, a comment on invertibility of this matrix. So we mentioned E has a rank of 2, therefore it is singular and not invertible. Now imagine if you were given the epipolar constraint and asked to work back to get the lambdas. Okay, so do you remember that we had the lambdas there previously and we've taken them out? So let's say you've got your epipolar constraint, can you work your way back? And you can't do that, and that's because you now have a 0 on the other side of the equation. Now what this should tell you is that you have lost some things along the way. So in order to get rid of our 3D coordinates, which were interlinked with our rotation and translation altogether, we've had to give up some information. So we've done some projections onto, by multiplying by those different vectors, we've actually done projections onto them, which means we've lost things that were in directions other than those vectors. So you may remember that rotation and translation had 6 degrees of freedom, and you might assume that if we're going to figure out the 6 degrees of freedom, we might need 6 equations, or that might mean that we need 6 sets of correspondences. But we actually can't get away with that now because we've lost some information. So we will actually need 8 sets of corresponding points, and hence this is called the 8-point algorithm. So going back to some of the questions I think Vin was asking earlier, how do you decide your reference point? We're actually going to need lots of them in order to try and figure this out. We can't get away with just one. We're going to need at least 8 of them, and we're going to have to hope that those 8 are good ones. If they've got noise in them and so on, that leads to problems down the line. And this is where this neat mathematics problem becomes a good bit tougher. So that's obviously why we call it the 8-point algorithm as well, which we mentioned earlier. So this is all great, but the truth is that the epipolar constraint is not really a nice identity. So E is a 3x3 matrix. If we find enough point correspondences, we should be able to recover E, but then what do? How do we separate it out into the rotation and translation, because that's what we want to know. So we don't really want E, we want R and T, so that we can tell how the camera moved between frames. How do we separate out R and T? Well, the space of all essential matrices is called the essential space, and it's defined as follows. It's made up of the rotation, which is a special, or in the special orthogonal group 3, which means that it has a determinant of 1, that rotation matrix, and the translation is in R3. Okay, now the problem is that that determinant of +1 for a rotation matrix, as we mentioned many lectures ago, is a problem when it comes to trying to actually zone in on exactly what is the right decomposition of this. So a non-zero matrix E, so just as long as it's a 3x3 that isn't full of zeros, is an essential matrix if and only if E has a singular value decomposition of the following. E is equal to U sigma V transpose, with the following. The sigma, which is a diagonal matrix, has to have the same 2 singular values and then a 0. Okay. Now, singular values and eigenvalues are not exactly the same, but you can think of them in a similar sort of a way here. And what this is basically saying is that if you thought of these as eigenvalues, that the 2 of these would have to be the same, and that one of the eigenvalues would have to be 0. Now, if one of your eigenvalues in a 3x3 matrix is 0, that tells you that your determinant is 0, because obviously you multiply all the eigenvalues together to get your determinant. And it tells you that obviously your one of your eigenvalues being 0 means that you're obviously dealing with a two-dimensional plane. So you can see how this all is all wrapped up together. Make sure you do go and look up singular value decomposition so that you see that. So for some sigma value, which is bigger than 0, obviously because 0 isn't going to do the job, U and V are both rotation matrices. Okay, so if we do a singular value decomposition like this, and we can get those both to be the same value, then and this to be 0, then we can be assured that we have some rotation matrices, and from that we can work out our rotation matrix. So this is from a 1989 theorem, which I'm not going to go through the proof of or anything like that, called characterization of the essential matrix by Huang and Forgeras, who I think have a book by one of those guys up on the shelf there. And it poses quite a problem because the space of essential matrices is a nonlinear one. So solving it in the normal linear algebra way will find us a 3×3 matrix, but it's unlikely to have these properties. So to add insult to injury on this one, even if we find the essential matrix, there are two possible decompositions for the rotations and translations. So one bit of good news is that in general, only one of the decompositions makes sense. So if you do the decompositions, you can test them out, and only one will give you positive depth values. The other one will give you negative depth values, suggesting that the thing is behind, you know, that the whatever it is behind the camera instead of in front of it, which clearly couldn't be correct. So this is from another theorem, and again, I'm not going to go through the proof of this. And this is how you break up the relative poses from the essential matrix. So what you do is you do that singular value decomposition there, and once you have that, you can use the different parts of this within some formulas here. So in the first case, and these are our two possible ones that we can have, rotation 1 and translation 1, or rotation 2 and translation 2. As I say, only one of them will turn out to be useful. What you do is you take your U matrix, you do a rotation around Z by pi over 2, okay, which we saw in earlier lectures how you would do a rotation around the Z axis, so the cosines and the sines that you would put in there. You use your sigma there, and you use your U transpose there in order to figure out what the translation would be in the first case. For the second one then, what you're doing is you're using again a rotation around Z of pi over 2, or in these ones, the only thing that changes between these is the rotation around Z effectively. And you then use a V transpose there in order to find out which rotation matrix is going to be. Okay, so that's how we would get it once we get our essential matrix, if we can get it. Okay, so getting an essential matrix, how do we do it? As mentioned earlier, our standard linear algebra methods will recover a 3×3 matrix, but this is unlikely to meet the stringent criteria of an essential matrix. So we have two options. Firstly, recover whatever 3×3 matrix we can from our linear methods, and then project that onto the space of essential matrices. Okay, so we in some way project it onto the space, onto this nonlinear space from whatever result we get. So in other words, we use the closest essential matrix to the one we recover. Whatever closest means, because of course this is an unusual space, it's not a proper metric space. So this is easy, but it lacks accuracy. But this is nonetheless the approach we're going to use, right? The other way is to optimize the epipolar constraints in the essential space itself, where you try and find a solution by kind of your least squares methods or some of those other optimization techniques, and you try and do that penalizing the determinant if it's more than +1 for the rotation, and so on. So trying to keep those different things into account. That's much more difficult, so we're not going to look at that at the moment, but we may come back to some of those techniques, not necessarily to do with the essential matrix, but we may come back to some of those techniques later in the course. We're going to use the first one, which is that we're going to do linear algebra, find a 3×3 matrix, and then what we're going to do is we're going to get it to the closest essential matrix from there that fits the criteria. So to do this, we're going to use the 8-point algorithm. So we start with the epipolar constraint, which is, as we've shown it before, this E is made up of the translation and the rotation. And this should hold for any matching points x1 and x2 in two image views. If we have enough points, we'll use 8. We're going to use 8. Then we should be able to recover the unknown matrix E. Strictly speaking, we can get away with 7 points, but 8 will give us a unique solution up to a scale. This assumes the 8 points meet certain criteria and have no noise. And of course, they will have noise. But anyway, so more on this later. So E is a 3 by 3 matrix. So we'll write them out as this E11, E12, E13, all the way down to E33 down here. And what we're going to do is we're going to stack them all into a vector. So we're going to show them as a 9 vector here, a 9 by 1 vector, and we list them in this order. Now this is perfectly fine to do. Somebody else has gone and figured out exactly the order to go and put them in order to do this, but it just makes it a little bit easier when it comes to doing the breakout of the thing. So for each set of point correspondences in homogeneous coordinates, we will get one linear equation in the unknown entries of E. And as I say, we're going to need 8 of them in order to try and figure out a result. So for example, and this is where I mentioned that I changed from having x1 and x2 to being x and x prime. And the reason for that is that what we're going to then say is we're going to have 8 point correspondences, and they're going to be the x1, x2, x3 and down to x8. So in our first image, we have x, and this is going to be made up of x, y and 1, so it's going to be in homogeneous coordinates. And then x prime is its position in the second image. So that's x prime, x prime and y prime. Okay. So don't get confused by this notation here. Those are not the same things. It's just that's how we tend to do it. We tend to encapsulate everything into one of these. Okay. So this is a vector, whereas this is just an individual position here. So what we can do is we can actually, and this is what would happen if you multiplied out the 3 by 3 by the 3 vector, you'd get something that looks like this. Okay, and we'd be saying that this is equal to 0. So what we can do is we can actually split up these parts here. Remember that this is x prime from there, and this is the x from up here in each of these cases. So we can write that out as a vector like this. And so basically what will happen is that this will get multiplied by this, and what we're saying is that that will result in a value of 0. So what we then have is we put 8 of these together. So we've correspondence 1, correspondence 2, all the way up to correspondence 8. And what we now have is an 8 by 9 matrix. And I was saying there just before we had the crash that if this was a 9 by 9, it could theoretically have a rank of 9. Okay, but this is only an 8 by 9, so the best we can hope for is that we have a rank of 8, which leaves us with a null space. And I see a few people putting it in there. Now Vin has it wrong at 4, but the null space of 1, because it's what's left. Okay, so if we take 8 away from 9, it's what's left. Now if we have a null space of 1, what that tells us is that there is a single vector that is in the null space of this matrix. So this matrix here, sorry, including that, has a null space of 1, so it has a single vector. And what we're hoping is that that vector is this one here. In fact, that's what we're specifying here. We're saying that this is the only vector in a 9-dimensional space that will map to 0, apart from if this was all zeros. Okay, that would also map to 0. Okay, so that's what we mean by the null space. Now, the thing is that gives us a vector. It doesn't tell us the length of that vector. And so that's why we continue to lose a little bit of information in terms of scale. We're not entirely certain maybe where along that vector it is. But from this, we at least get a result. Now, this is something that shows up again and again and again, where we try and solve something by what its null space is and therefore what its vectors are. Okay, so that's the idea. So guys, we've gone up in the hour there. Are you okay to continue? There's only another 5 slides to go. Are you happy enough to continue without a break? Yeah. Okay. And by the way, you feel free to ask questions. Obviously, as I say, we have plenty of time. So why 8? So you'll notice that there are 9 unknowns in E, but as mentioned earlier, we can only determine a unique solution up to a scale factor. So generally, we set E33 to 1 so that we can set it, because we can set it to any value, but we must do this first before we start. So you can't just set it to 1 later, okay? You set it to 1 at the beginning, and then everything else is in relation to that. for E to have a solution, A must be of rank at most 8. If it is of rank 8, then we will have a unique solution. So this is A, by the way, this is the A matrix, in case I didn't specify that. That's the A matrix there, the big 8 by 9 one. So if A by E stacked there is equal to 0, this says that, that the vector ES is in the null space of A. So if A had rank greater than 8, then there would be no null space and therefore no solution. So for less than 8, for example 7, there would be, that should say a whole, not a hold. There would be a whole 2D plane of solutions, because there would then be a null space of 2. Okay, 7 away from 9 gives us 2. That's 2 vectors, and 2 vectors can make it a whole plane. And now I've got a bit of a problem determining where it is. Now, as it turns out, you can do that with, there can be ways around that, but the easiest solution for us is to use 8-point correspondences and try and get it. So there are methods to determine the solution on this plane with the best essential matrix in the E space. Now, there's a problem here. Now, I have one line that's bold lettering here. That's the most important line from this. The rest of it is me just covering myself, that I'm mentioning a load of other things to you, right? But the thing to mention here is that if the data, the point correspondences, are not exact, and it won't be exact in the real world because there's all sorts of noise that can happen and there's distortions in the lenses and so on, the rank of A may be greater than 8. What that basically means is that that noise can creep into your null space, and once it does, you no longer have a null space, because it's like if I've got a sheet of paper here and I have noise, the noise is not necessarily sticking to the paper, it could often be sitting up off it, and it means that I can no longer find a vector that's outside of that. Okay, that's the most important thing for you to remember, but there's a few things here just to kind of state as well. 9 is the full rank, as there are 9 columns. In this case, we can find a least squares solution if we wanted to. Okay, so least squares doesn't get us exactly to 0, but it gets us close. Okay, and as close as we can go. This is also the case if we use more than 8-point correspondences. But also note that even in the supposed full rank case, where we have, you know, a 9 by 9 matrix or more, we would need 9 correspondences in order to realize this. Okay, so we'd need a 9th one in order to do it. So in the case of noise and only 8 points, we will still only have rank 8, but our null space could be the wrong vector or the wrong line. In other words, it could send us wrong by doing that. Okay, that said, the first point is the most important one, which is that noise can screw up our null space and means that we don't find a vector in that null space. So how do we go about finding the thing? Well, what we do is we do a singular value decomposition of it, which is, again, as I say, quite similar to finding eigenvalues, and we should find that one of the singular values is 0. Okay, now if we find one of the singular values is 0, that's the vector that's associated with that is our vector that's in our null space, because it has a singular value of 0. Okay. So what happens is that when we do a singular value decomposition of this, each one of these will be 9 by 9 matrices, and this sigma one in the middle, it will look like this. It'll have sorry, I'm saying that wrong. I said 9 by 9 there, but actually what we've done is we've changed ES back to its 3 by 3 view. So these are 3 by 3 matrices, right? So what's going to happen is, am I correct in that actually? Yes. No, sorry. I've gone and put myself wrong. It's a further thing I'm thinking of. Sorry, so this is the SVD of A. So these are 9 by 9s. So that sigma in the middle that we're using is going to look like this. It's going to have singular values on the diagonals here. Okay, so sigma 1, sigma 2, sigma 3, ... all the way down to sigma 9. Okay, everything else all in here, all zeros. Okay, now what we do is we find which one of those is 0, and if one of them is 0, that means that the vector, okay, the vector in our V transpose, which again is the 9 by 9, so we look through the columns at that and we find the column that's associated with that, that is the ES that we're looking for, the 9 by 1 that we're looking for. Now, when we do singular value decomposition, and you can do this in NumPy, or you can do it in NumPy, which is part of Python, or you can do it in MATLAB. When you do a singular value decomposition of the thing, what it does is it doesn't just do this singular value decomposition, it reorders these sigmas so that the largest one is here and the smallest one is here. Now, if it's the smallest one, clearly the 0 is going to be the smallest one, so therefore it would always be in this final position if you use a software program, and that means that you're always looking at the final column of this V transpose in order to, of V, obviously it's V transpose here, but you look at the final column of V, and that will give you the vector that you're looking for. Okay. So most programming software libraries will order the singular values in descending order. Beware, if you just do that as ordinary maths, that's not guaranteed, and some software libraries may not do it. So when you see things where people say, just use the last column, you need to be aware this is what they're actually doing, and they're assuming that it's been ordered. So in that case, the solution ES will be the final column of VE transpose. So as we mentioned, calculating E by this manner is unlikely to get us a matrix that obeys all the constraints of the essential space. Instead, we must project onto it. So when we get our E, that's to do with that, what we're going to do is we're also going to do a singular value decomposition. This is where I was getting confused with the last slide. So we're going to do a singular value decomposition of E now. These are all going to be 3 by 3 matrices rather than 9 by 9 in this case. And what we're going to do is we're going to do the singular value decomposition, and we'll probably find that these are all non-zero. But if we've ordered them, this one will be the smallest and hopefully close to 0. Okay, so we hope that that's close to 0, and what that basically means is that what we're going to do, just to map it to the space of the essential space that we want, is we're going to just set it to 0. So we're going to just truncate it down to 0 from whatever it was, and what we're going to do is we're going to take these two values, lambda 1 and lambda 2, we're going to add them together and divide them by 2 to make sure that they're the same value. Okay, now if this seems a little bit you know, like we're not treating it with care, this is probably the best way we have of getting from the essential matrix that we've, or the E matrix that we've got, mapping it down to the actual nonlinear space that we have, the closest one. So this will do reasonably good, but just not perfect. So we call that E star because it's not exactly the essential matrix that we should have. It's the closest one to the one that we've worked out by this method. Okay. And once again, once we have that, you can then from there work out your rotation and your translation. Now I'll go ahead with your question if you have one there. There's no problem. I can go back to it. So we have our rotation and our translation there again. We can figure it. That's okay. So we can figure it out from these once we have it. Okay. So maybe just we're at the end there, but maybe just go back to our original idea here, which was what was our route to a solution. So what we wanted to do was we wanted to disentangle our 3D coordinates from the camera motion. So we separate them out. We want to remove the 3D coordinates from the algebra so that we have equations in the 2D image coordinates only. We then use that to solve the camera motion. This is where we use the 8-point algorithm. And we now have the extrinsic parameters by that last slide there, which was a repeat of the slide previously. We now have the extrinsic parameters, and from there we can start to work out where in the 3D world are they. So if you remember in the beginning we said that if we have the rotation and translation, we can figure out the 3D parameters, and if we have the 3D coordinates, we can figure out the rotation and translation. We've now got the rotation and translation, so next week's lecture is about how we can reconstruct those. Okay. And just to go back to some of the, just to remind you of some of the assumptions for anybody who was maybe late in, we were assuming tonight that we're viewing a static scene. So nothing in the scene is moving in this assumption, okay? So we're viewing a static scene and we have two different views of the scene. we're assuming that we already have a set of point correspondences. So again, you know, the questions that come up about, well, how do you decide the point correspondences? They're for a different lecture. So where you were working on the assignment there for doing the Harris and Sheehan Massey and all those, for finding good point correspondences that might be unique to each other, that's where you did those. And obviously there are better ones, then there are better systems that have come along since. So we're assuming in this one we already had those and that we've got 8 good ones. Okay, we can use more, and in most cases we will use more, and that's perfectly fine. But that's what we're assuming, that we already have those. And we'll assume that the intrinsic parameters of the camera are already known to us, and you've seen that we simplified those. So in next week's lecture, what we're going to look at is, from that, how do we figure out what the 3D coordinates actually are? What would happen if we didn't know the intrinsic parameters of the camera as well? And what are some of the problems that could occur? So how do we pick 8 good points? Because there are certain configurations of the points which are not good. They're called degenerate configurations. In other words, we get 8 good points, but it turns out that actually you know, they're all on a plane. In 2D space, which of course can happen to us quite easily, so that can cause us problems and so on from there. Now it can also be a good thing if we know that it's a plane. So there are some of those configurations that we look at, and we'll have to have a think about those. But try and think of this lecture just entirely confined to the fact that we've got 2 views, we've already got our point correspondences. How do we figure out the rotation and translation from there? Okay, and we'll continue on with more of it last week. Just for anyone that was in late for the first few minutes, what I was saying is that we're probably 2/3 of the way through the material for the course, so we're going at a good speed, and I'm going to be able to throttle it back, that we're only using an hour or a bit more to get through most of the lectures from here on in, so that should hopefully ease things off on you a little bit. Okay, if you have any questions there, feel free to fire them at me. We've got plenty of time. That's okay, no problem, Daniel. So facial recognition, of course, is a slightly separate problem, but you've come across this before, have you, in facial recognition, the 8 points, have you? Yeah, I mean, it's in terms of facial recognition, you've got a slightly different problem there normally in most cases, in that the person probably needs to move rather than the camera moving. Okay, so you have a slightly different thing. So rather than the camera moving, the person is moving. And if you can make sure that that a move has taken place. Now this isn't something that I'm that clued in on, right? But if you can do that, then the same sort of things are going to apply. But of course, you're trying to determine something about rotation and translation now of the person rather than the camera. How most facial recognition is done on the likes of mobile phones, like for turning it on and so on, they are actually sending out a pattern. So they send out a pattern in a non-visible part of the spectrum. I'm not sure what part of it is, with points on it, and from that they can actually determine the deformation of those points. They can actually figure out the geometry of the face for facial recognition, so that they're not just looking at a 2D image and that they can pick up a 3D. So it's a slightly different thing, but those ideas may start to come into autonomous vehicles as well, where they actually send out a kind of a light and try and figure things out from there. But Apple are the big people when it comes to doing that. Yeah, so LiDAR is quite a similar idea. So this obviously works over a kind of a shorter range, and what they do is they'll put out a full pattern rather than just a point and recording the distance back. So they put out a pattern, the camera can see it, and they can see the deformation of it, and from that they can figure things out. So a slightly different problem. Okay. So guys, I'll say good night if there's no other questions. Okay.